Hi, welcome. Today we're going to continue talking about option D, and today we're going to start with the higher level part of the material. And I would like to talk a little bit about chirality and how chiral molecules in medicine are going to be very important. And so we're going to focus on the case of Taxol as an example for chirality. Now, if you may recall, we've discussed that chiral substances exist in the body. Every single one of our proteins uses chiral amino acids. All right, the sugars that we consume are chiral, and we use only a particular type. We are able to digest only a particular enantiomer of those sugars. Now, chirality or optical activity exists because we have an asymmetric carbon. Generally, we're going to speak about carbon at this level. There are other sources of chirality which are beyond the scope of this class. Now, a chiral carbon or an asymmetric carbon is one in which a carbon has 4 different substituents in its immediate surrounding. All right? Now, because the body is chiral, the way that it interacts is like hands. There are certain handshakes that make sense, other ones that just do not. All right? And so that requires chemicals that are going to act as medicines to have a particular as well chiral environment. So the sterics, so the interactions that they can have between them can actually result in the desired products, and it's not going to give us troubles like those that we have discussed for thalidomide. All right? So if we have a protochiral or a prochiral substance, such as this one, here we have a carbon that has 3 substituents around it, all right? Something like an aldehyde or even a ketone could work there, all right? When we add to this side, we're going to get 1 enantiomer. All right, when we add to the other side, we're going to get a different enantiomer depending on what groups we're adding. All right, if we do not select for this, we are going to get what is called a racemic mixture. 50% is going to be added on this side. 50% of whatever we're adding is going to be added on the opposite side, giving us both enantiomers in equal amounts. That mixture would have 0 optical activity because the rotation for each enantiomer would cancel each other out. All right, so this is the kind of structure that we have in the reactions such as this one. All right, so we would have addition, for example, a Grignard addition or addition of an ethyl group, for example, all right, to this ketone would happen from either the top side or the bottom side to give us these carbons that have optical activity. All right, but because they're formed in equal amounts, the mixture, the racemic mixture, will have 0 optical activity, 0 optical rotation of the plane polarized, of the plane of plane polarized light. All right. So, how can we do this? How can we make it happen such that we can create one enantiomer over the other, or how can we purify them? Well, if we have a racemic mixture, all right, one of the simplest things that we could do is we could pass this through a column, all right, and that column, if that column has a chiral material in there, it will bond to one substance more readily than the other, and therefore, as you flow your racemic mixture through it, through the column, through the chiral column, you will separate the 2 materials, the 2 enantiomers, because one of them will stick more to the column and therefore come out of the column later. The other one will stick less and come out quicker. So you separate this by what is called retention times. All right. This is a possibility, but it can be very costly. It can be very wasteful because you have to put a lot of solvent. You may have to run this material several times through the column to actually separate them to get a reasonable amount of enantiopurity, because sometimes the separation is very small, so you're going to continue getting mixtures, so you would have to run this several times. A better method to do this is that rather than forming the racemic mixture, all right, is that you add some type of asymmetric auxiliary, all right, to this compound in order to create a chiral compound. We normally use a natural product, something that is going to be cheap, that nature has made for us, that we can put there and that will block one side from being reacted upon. Let's say that we had this compound one more time, okay, and I'm going to try to get this open for you guys to see it completely. All right, if we have this, we could attack from either, for me, the right side or the left side, okay, because we have no chirality in the rest of the compound. Now, I am simplifying this a little bit, but if we bring a chiral auxiliary, some type of large molecule that normally is a natural product, all right, and we added to form a particular enantiomer, and only one enantiomer, well, what this may do, depending on its rotation, and let me get it rotated properly, all right, if we have it on this side, it makes it very difficult for addition to happen here on this direction. But because this other side is open and doesn't have the sterics of this bulky group auxiliary that we have added here, this chiral auxiliary that we have it here, the attack is going to happen almost exclusively from the right side. Again, from my view, the right side. All right, and therefore give you only one enantiomer, produce only one enantiomer, or produce primarily one enantiomer. There may be a small amount that gets produced by having addition on the other side, but mostly it's going to be happening from this side. Use of chiral auxiliaries is a wonderful way to make compounds that will be enantiomerically pure. So for example, if we had added, and I'm just going to open it like this, don't worry about how the bonding happens, all right? If I had made it like this, and let's see if I can make that bond, we have made only one enantiomer. This carbon, as you can see, has 4 different substituents, okay? The red one, the blue one, the white one, and the black one, all right? And so later on, I can treat this to remove again that auxiliary. That auxiliary can be recycled, used again, so that's normally a good thing to be able to do. And voila, we get a single enantiomer being produced, all right, rather than producing both of them. And this allows us then to have a compound that is more pure and therefore have the right activity for what we want it to do, all right? So this kind of can be observed in this type of image that I have down here. Here we have our protochiral substance, okay, substrate. And so we are going to first add the chiral auxiliary. So the first process on the first step in using the chiral auxiliary is to add the chiral auxiliary to make a particular enantiomer, all right? Now, this will favor addition in only one direction, all right? When we have this particular addition, only one side was made. And then afterward, we can remove that auxiliary in order to regain the actual target molecule that we wanted to get. All right, the chiral auxiliary can be recycled, but the most important thing is that we have made enantiomerically pure only one of those products that we want. Okay, so that's going to be very important. Now, how does this apply to Taxol? Taxol, or paclitaxel, sorry, I cannot say that one very quickly, all right, is an actual drug medicine, all right? The Taxol can be naturally obtained from the Pacific yew tree. Now, the Pacific yew tree is a very rare tree, and the extraction process was very labor intensive, very expensive, and yielded very small amounts of Taxol. So small that it would make it not practical as a source of Taxol for treating cancer patients. All right. Now, what chemists were able to do was to actually find, and here's the actual structure of Taxol. By the way, you can find this in your data booklets in table 37. All right. Taxol contains 11 different chiral centers. I've circled them ahead of time here for you. Here is a three-dimensional drawing of how it would look. It is very important to see that we can recognize all of those 11 chiral centers in Taxol. All right. Now, Taxol itself can only be obtained from the Pacific U tree, but a related compound, all right, can be isolated in greater amounts from the much more abundant European U tree, and it can be removed rather than in the Paxol, where you have to take it out of the bark, which kills the tree. The precursor can be obtained or can be extracted from the leaves of the Pacific yew tree. So therefore, it's something that does not kill the tree. All right, but it is not the final product. And so, in order to actually make the chiral centers that are required to finish Taxol from the precursor, a chiral auxiliary, in this particular case, trans-2-phenylcyclohexanol, all right, which we have drawn over here, which has two different chiral centers, is used. Now, because of the shape of those particular chiral centers, it actually blocks one of the sites and makes exclusively one enantiomer when we react it, and therefore allows us to synthesize in much greater yields, in greater purity, and much cheaper than actually killing Pacific yew trees, therefore being more sustainable, this particular drug. All right, so this is very important. The trans-2-phenylcyclohexanol can then be recycled when it's removed from the compound, and therefore can be used again, decreasing the price of also the synthesis of this compound, because enantiomerically pure auxiliaries tend to be quite expensive. All right. If we want to test and check for how enantiomerically pure a substance is, we are going to use a polarimeter, just like we talked about in organic chemistry when we're talking about the measurement of optical rotation. All right, we need plain polarized light, and we need to use the polarimeter. You have another video for this. We've talked about it in class with you guys, so I'm going to go ahead and move on to the actual measurement part. All right, one more time to remind you, we are first producing unpolarized light, which will pass through our first polarizer, all right, to create plain polarized light, in this particular case, vertical polarized light. That light will shine through a polarimeter tube, which contains your solution of your substance. When it comes out, it will have a plane, the plane of polarization will have been rotated, all right? And so we need to move our analyzing polarizer in order to measure the degree of rotation. All right. Now, based on that degree of rotation and knowing what it should be for the optically pure Taxol, we can make a ratio and therefore find out what percent pure enantiopurity do we have of the compound. And again, here is the image that I've shared with you before for how the polarimeter works. Again, as it dissolves, as it travels through the solution, it's going to rotate more and more. And that's why we have a particular length and concentration for the solution, because it is going to depend on that. There are 5 total factors that cause different rotations of our plain polarized light. Obviously, concentration. The more concentrated it is, the more rotation you're going to have. The solvent is surprising, but the particular solvent that you have will have greater or less interaction with the plain polarized light. 3, the particular type of frequency of the wavelengths, or the wavelength or frequency of light that you're using, because different frequencies will interact more or less with the different bonds in the chiral molecule. The length of the path, okay, and finally the temperature. If you have more, if it's hotter or colder, you will have more or fewer collisions and rotations of the molecules in there that will then change our light. All right. The angle of rotation, alpha, can be determined by specific angle of rotation, which is some constant for that particular substance, all right, times the concentration times the length of the path. So by doing this, we can actually find what this rotation is, and this is a very straightforward idea. So Taxol, a wonderful anti-cancer drug that requires it to be enantiomerically pure in order to be active. We cannot sustainably extract it from natural sources like the Pacific yew tree, and therefore we rely on asymmetric synthesis by the use of chiral auxiliaries in order to be able to get sufficient amounts. All right, thank you.